Welcome to Introduction to Geographic Information Systems. This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program. In the past it has been said that a GIS has 5 components you need to make it work, but now, it is closer to 3.5. You need software, which we have discussed. You need a person, which is you. And you need data, which is what we will cover today. What are the other 2 components? Storage and hardware. Storage used to be a significant issue as GIS datasets were quite large, but now the price of storage has fallen so much that you can get a 5 terabyte hard drive for around 100 these days. Storage is now no longer a consideration. Usually, there are of course exceptions to this. The same for hardware. When we downloaded QGIS we did not discuss specifications of the computer needed. That is because QGIS can pretty much run on any computer by itself. The hardware needs is determined by the size of your dataset. If you are using terabytes of data then you will need a powerful computer to handle it, but if they are small datasets, even old computers will work, though they might be slow. So really, you only need to think about 3 or so components, unless you are working on a project with huge amounts of data. So what is the data you use in GIS? To recap what was discussed in the introduction, GIS deals with geographic data, a type of spatial data. Geographic data refers to locations on the Earth's surface or locations relative to the Earth's surface, like atmospheric pressure at a particular location. Spatial data refers to any locational frame of reference. Geographic data is just one form of spatial data. Other spatial data could be photographs or even X-rays of your body. X-rays show spatial relationships between your bones. What is the difference between data and information? Why is it not called geographic data systems? There is a significant difference between the concepts of data and information. Data is a set of values or elements used to represent something. For instance, the string of numbers 1.2.3.4.5.6.7.9 is data. Generally, data refer to facts, measurements, characteristics, or traits of an object of interest. Once data are put into context, used to answer questions, situated within analytical frameworks, or used to obtain insights, they become information. For our purposes, information simply refers to the knowledge of value obtained through the collection, interpretation, and/or analysis of data. So geographic data, which is what GIS uses, is a set of facts, measurements, characteristics, or traits of locations on the Earth's surface or locations relative to it. It is important to note that all data is abstractions of reality. The data you use in GIS is meant to represent real-world phenomenon. How you represent it will depend on what it is you are looking to investigate. Given the complexity of real-world phenomena, our representations of it can never be perfect. We have limitations on the amount of data that we can store, limits on the amount of detail we can capture, and limits on resources. Moreover, we have limits imposed by the GIS itself. How do you represent complex 3D real-world phenomenon on a 2D screen? Well, let's explore that. Geographical features can be either spatially continuous or spatially discrete. A discrete object has known and definable boundaries. It is easy to define precisely where the object begins and ends. A house is a discrete object easily defined by its walls. Other examples of discrete objects include rivers, roads, and land parcels. Discrete objects are usually nouns, a person, a place, or a thing. A continuous object represents phenomena where each location on the surface is a measure of the concentration level or its relationship from a fixed point in space. That might sound a bit like gobbledygook, so let's look at an example of a continuous object, elevation. It is the fixed point above sea level. You can continually measure elevation all around the globe. There is not a single location where elevation doesn't exist. It might be better to think of it as the opposite of discrete date. Does it have an end? No, then it is continuous. Surfaces are continuous objects, such as elevation, rainfall, pollution concentration, and water tables. Continuous data is also referred to as field, non-discrete, or surface data. How can we represent such features in GIS? It is said that all geographical phenomenon can, in 2 dimensions at least, be represented by 3 basic entity types. Those are points, polylines, and polygons. A point is composed of one specific location. Points are the most basic geometric primitives having no length or area. By definition a point can't be seen since it has no area, but this is not practical for our needs. So points in GIS are represented using symbols that have both area and shape, like circles and squares. You have to be careful how you represent points so that you and other people can understand them as points and do not think they are polygons. A polyline is composed of a sequence of two or more point pairs that are connected to each other. Like a point, a true line can't be seen since it has no area, but in GIS a line is symbolized using shapes that have a color, width and style. Roads and rivers are commonly stored as polylines in a GIS. Again, you have to be careful with using them as representations. A person might confuse the width of a line meant to make it visible with the actual width of the object. Finally, there is the polygon. A polygon is composed of three or more line segments that are connected continuously. All the segments of a polygon must be connected with no breaks. Polygons do have area and can be accurately represented on GIS. Conceptually, geographical data have several components. 1. A location component. This is a description of where it is in its geometric/geographical extent. Is it a point, line, or polygon? This is what makes the data geographic or spatial as opposed to other types of data. You cannot have geographic data without this component. The second component of the data is the attribute. This is information describing the geographical entity. Where the location component is concerned with defining the location of the object of interest, the attribute component is concerned with its non-geographic traits and characteristics. To illustrate the distinction between location and attribute components, think about your home where you grew up or where you currently live. For instance, we can define the location of your home many ways, such as with a street address, its postal code, or its GPS coordinates. That is the locational component. In addition to defining the location of your home, you could also include information such as the number of bedrooms in your home, the year it was built, or the number of people living there. These attributes tell us a lot about your home but relatively little about where it is. Attribute data can be broken down into 4 measurement levels. Nominal scales are used for labeling variables, without any quantitative value. Nominal scales could simply be called labels. A good way to remember this is that nominal sounds a lot like name, and nominal scales are kind of like names or labels. With ordinal scales, the order of the values is what's important and significant, but the differences between each one is not really known. For example, is the difference between okay and unhappy the same as the difference between very happy and happy? We can't say. Ordinal scales are typically measures of non-numeric concepts like satisfaction, happiness, discomfort, etc. Interval scales are numeric scales in which we know both the order and the exact differences between the values. The classic example of an interval scale is temperature because the difference between each value is the same. For example, the difference between 40 and 50 degrees is a measurable 10 degrees, as is the difference between 50 and 60 degrees. Ratio tell us about the order, they tell us the exact value between units, and they also have an absolute zero. Good examples of ratio variables include height, weight, and duration. While the locational component is required for GIS, the attribute component is what makes GIS really powerful. You can attach an almost unlimited number of attributes to a location, which allows you to run an almost unlimited number of analysis. Moreover, multiple pieces of data can share the same locational or attribute components. What makes GIS very useful is that you can group types of data into layers, even if it refers to the same location. The information about different variables can be stored separately into thematic blocks of data. In GIS we call these thematic groupings of data layers. A layer can be just about anything. It could be all the rivers in your study area. It could be all the buildings. It is whatever you find helpful in organizing your data. All the information that we will use in a GIS will be in the form of layers. They can be used independently or with other layers. One popular way to describe and to visualize a GIS is picturing it as a cake with many layers. Each layer of the cake represents a different geographic theme, such as water features, buildings, and roads, and each layer is stacked one on top of another. This is also very helpful when creating visualizations, as you can add and remove layers from your output. If your users don't need to know where the rivers are in your map, hide that layer from the output. It greatly improves your visual presentations by removing unused information. You should get used to thinking about the data you will use in GIS as layers. If you are downloading very large datasets, you will also run into the concept of tiling. This is where larger datasets of multiple layers are broken down into more manageable units to work with. You will especially find this with countrywide datasets. Rarely are you able to download all the data for a whole country from the internet, as it will be too large. So lots of online data repositories tile their data and allow you to download it in chunks. Vector versus raster. There are two primary data models for storing and organizing the locational data in GIS, vector and raster. Let's start with raster. A raster data model uses an array of cells or pixels to represent real-world objects. With each cell, some value is associated to characterize that part of space. Sometimes, the word grid is used to describe this, but strictly speaking, a grid refers to values at the intersections of a network of regularly spaced horizontal and perpendicular lines. It is important to note that a tessellation is the subdivision of space into a set contiguous tiles or cells which in combination occupy completely the space, leaving no gaps in between them. This is a key distinction between the vector model. Implicit in a raster data model is a value associated with each cell or pixel. Even the representation of empty space between two discrete objects needs to have data defining it as such. There are two types of tessellations. 1. Regular tessellations, which can be squares, triangulars, and hexagonal. The square cell tessellation is by far the most commonly used, mainly because georeferencing a cell is so straightforward. These tessellations are known under various names in different GIS packages, but most frequently as rasters, and this is the common term used throughout the GIS world. An important advantage of regular tessellations is that we know how they partition space, and we can make our computations specific to this partitioning. This leads to fast algorithms. An obvious disadvantage is that they are not adaptive to all geographic phenomenon we want to represent. The cell boundaries are both artificial and fixed. They may or may not coincide with the boundaries of the phenomena of interest. The second type of tessellations are irregular ones. This is the same irregular tessellation in that they subdivision of space into a set contiguous tiles or cells which in combination occupy completely the space, leaving no gaps in between them, but they differ in that the cells may vary in size and shape, allowing them to adapt to the spatial phenomena that they represent. Raster data can be used to represent points, lines, and polygons. However, as discussed with regular tessellations, you might get pixelation, where the representation is not precise. If terms like pixels and pixelation sound like photography to you, that is because there is overlap between the concepts. If it helps, you can think of raster data as photos, an image of tons of small pixels that make up a larger dataset. In fact, you can import some photo formats into a GIS as a raster dataset. It is a bit more complex than that, but not by much. Vectors. Tessellations do not explicitly store locations of the phenomena they represent. Instead, they provide a location of the lower left corner of the cell. A vector model stores explicitly georeference coordinates from some geographic space, and is also known as a vector, thus the name. In vector model, a point is just that, a single coordinate. A line in a vector model is a collection of two or more points, themselves specifically stored coordinates, that are connected. A polygon is the same as a polyline except that it is self-enclosing. Essentially, the difference between raster and vectors is how the data is stored and how it is structured to represent objects. So, which one is better? There is no right answer to this, and it is dependent on your needs. Remember, we have two types of geographic objects, discrete and continuous. Well, how do you represent continuous data with the different data models, for example with an elevation dataset? With raster you can assign an element to one or more cells and depending on the resolution can get very detailed presentations. With vector it is a bit more difficult to represent, and you can do something like contour lines. This can actually take up more computing resources than a raster model. It is actually much easier to use raster data to represent continuous data, and that is where it really shines. The converse tends to be true for discrete objects. With vectors to represent a square object, such as a building, it would only take 8 pieces of data to represent such an object in a vector model, 4 points and 4 lines. While, with a raster, depending on the resolution, hundreds of cells might need to be used. Vector data tends to be better for representing discrete objects. However, this is not a hard and fast rule. For example, a single cell in a raster dataset could represent a building, 1 data point instead of 8 for a vector model. This used to be of greater concern when storage and computer power was a problem. The most effective method for storing data was always a consideration then. For big datasets this is still a concern, but for a lot of everyday use, now, it is not so much. You can also convert between the two data models. It doesn't matter if you have some data in raster and some in vector. Moreover, the raster model has its precision limited by the cell size. Features smaller than that size cannot be represented. Also, shapes can be limited by the base unit of the raster. If it is a square, then it is limited to straight angles. It really comes down to what you want to do with the data and which model is best to support you in that endeavor. To recap what we have learned. Cover the important aspects defining geographic entities from a GIS perspective. We have discussed how we represent the data, points, lines, and polygons. We have also discussed the two spatial data models most commonly employed in GIS.